So basically, yeah, we will be talking about, and this being the last session of this hall, right? And this being the last day also, I told the Cypher guys to bring my session to first day, but they said the best should be the last one. So yeah, I mean, this will be the best session, right? Okay, so guys, what we will be discussing as of now, that all of the AI, you might have attended a lot of AI sessions here. All of this AI is passive AI. All of this AI has been passive AI. That is, you tell that AI to do something, it does it for you. So now we deep dive that what will be the future. We deep dive into a lot of challenges of this passive AI, what we have hit. And then I started exploring a lot of papers around it. And luckily, just in past 4 weeks around the same arena, there have been papers from DeepMind, Microsoft Research. So all of them are actually actively researching in this area. Because at one point, if you are building your own AI or you are fine-tuning any LLMs or any model diffusion models, you will hit a wall. That is, what to do next? Should I pour more money into it? What to do I? So yeah, I mean, we'll be discussing all of those things. Right. So a bit of introduction about myself. So myself, Anand Trivedi. I have a total of 11 years of experience solving codes and complexities, 7 years of dedicated experience in artificial intelligence. I have been one of the founding members of Aavenir. It's a 4-year-old startup now, based out of Ahmedabad in US. And we actually built source-to-pay solutions. To simplify it a bit, we make awesome contract lifecycle management along with artificial intelligence, accounts payable automation, that is again, touchless accounts payable automation, no human intervention required, and requests for proposal. These are the various applications that come under this suite. So we need to understand the current state of AI, that what is the current state of AI as of now. So all of the stories that you have been hearing around, and they revolve under 95% of AI is under this category. Is it really or not? Right? In fact, 95% of the business AI is at least in this category. Right? So we have natural language processing, computer vision, reinforcement learning, audio speech, graph neural networks, anomaly and risk detection. Now, apart from reinforcement learning, all of the other AI is passive AI. That is, it cannot learn on its own. It needs a lot of human effort to train it. Right? A lot of human effort is required to train this kind of AI. So, again, before I start discussing about the solution, I will be beginning with the journey that, how many of you are actually trying to fine-tune any model, pre-trained model for their own business use cases? Can we raise hands? Cool. Right. If not today, tomorrow you'll be doing it, right? Because that is ultimately one of the fine domain that AI has to go. For any business use case, you want to do it for legal text, medical text, customer support, whatever you want to do, you'll have to fine-tune it. Right? We cannot be using all the open AIs for a lot of extensive projects because that becomes too costly at the end of the day. And you lose security, that is, your data is going to their servers. And then you do not have too much of freedom to fine-tune them as per your requirements. So all of these models, I will be specifically talking about large language models. We could talk about a lot of models, but we will be talking about large language models with respect to businesses, right? So if we talk that these large language models fall into 2 categories basically. One is encoder model, the other is decoder model. So how many of you guys know about encoder and decoder models? Great, great. That's a lot of audience. So basically encoder models, I will make it really simple for all of you, so you do not need to worry about it. So basically encoder models are plain simple. As the name suggests, they convert any text into fixed size numerical embeddings, encoder models, right? While the decoder models then further convert the context embeddings into kind of, they generate the text from it. So basically, if you give any text, so ChatGPT, this is what it is doing. You give any text to the decoder model, it will try to generate the next set of words, set of lines and paragraphs for you, right? While encoder's model don't work like that. So the applications of both of these models become different. Encoder models are less GPU intensive, they're smaller, and obviously they solve a smaller area of problem. They can be used for classification, you can use for name entity recognition, these kind of applications you can use. While decoder model, they are usually the generative model that we see. The whole buzz that is all about the decoder model. There are certain models that use both encoder and decoder architecture, like T5 is there. It is using both of these architectures. Now, next, I would like to discuss is that I would give you a very fine and simplified version of, if you want to train your own model, what is the tech available to us as of now, right? I'll be sharing this whole slide with you guys, right? So what is the tech available for us now? So let's say I'll have to choose as per my requirement if I want to train an encoder model, or if I want to fine tune an encoder model, or if I want to fine tune a decoder model, right? It could be encoder model or decoder model. Now let's say if I want to fine tune any of them, I can choose to fine tune or from the scratch. Now, training it from the scratch is a very costly process. The cost can go from $1 million to $10 million or even more than that. Now, depending on the amount or the complexity of the problem, we choose if we want to train it from the scratch. Not many companies train from scratch, except if you're Salesforce or ServiceNow kind of big giants, then you might have this much budget for your AI. However, for normal companies, where the training budget is quite lower, less than 1 million and stuff like that. So basically, we choose that we can actually fine tune the models. So basically, when we say fine tuning the models, what becomes different? We need to understand this. What is difference? So, we came up, fine tuning, we understood the problem that you cannot retrain the complete models. That is, there are layers in the model. You cannot retrain all of those layers, right? So what we need to do is, so there are certain techniques such as PEFT, parameter efficient fine tuning. This is a technique that is actually, that reduces the cost, the time, and everything for training. However, the technique is that a model, what is a model? We need to again understand it. What is a model? So model is a big mathematical matrix or a tensor. It is a huge size tensor, what we call as weights. This is what is a model, right? And its size can be right from 40 GB, 50, 100 GB to 150 GB, right? These are called the weights, and this is what the model is. Next, what we can do is, first step is, we downscale this matrix. In calculus, there are various methods to downscale it. A common method used is matrix decomposition. I won't go into mathematics, right? Matrix decomposition, what we try to do is, we take up the complete matrix and the weights, and then basically we downgrade it a bit. So now we have smaller size model. We have the same model, similar capabilities. Some of the accuracy will be compromised, but much of the learning will still be retained. And then we can actually move for quantization. So quantization is basically changing the data types. Let's say whatever the data types you are using, you can downgrade those data types. And this is what is quantization is. And third, we start training the new version of the model now. The new version of the model, if let's say you are training 40 billion Falcon or Llama model, right? So basically training the complete model, let's say from the scratch, it would actually at least require, I have tried it with 100 GB of GPU, but it did not work even with that. But training it from the complete layers. But yes, I mean, if you try to train the same 40 billion model on, let's say, 24 GB GPU with these kind of techniques, it will be done like a charm. So again, you don't have to do all of these quantization and all of these stuff manually. There are wonderful libraries like QLoRa available to you. You can just give the parameters to it and it will do the job for you. And there are various other methods. I also wanted to mention that these are not the only methods. If you have searched online, so QLoRa is a very important thing. And you might have heard QLoRa here also. Many people might have mentioned about QLoRa. So there are other methods also by which you can actually perform distillation. You can freeze some layers, and then you can train the model. So there are various methods. But yeah, I mean, one first final step can be QLoRa for most of the use cases that we want to do. Then what happens? Now, this medical field, legal field, customer support, finance, these are complex fields to conquer by any LLM also, right? And then what happens is you start training it. Let's say you start training it via QLoRa. You have covered few use cases. And let's say I'll give you an example of our contracts field. That let's say you have trained the model over a set of contracts and it understands, it is actually detecting risks for you. It is detecting the risk for your business. And one day it happens to see an acquisition merger contract and it says that, you know what, I feel that this might be a risk, but I'm not very confident about it. That is, the confidence level has drastically dropped in this case. Now, the problem is that I will have to collect that feedback. I'll have to manually review it, and then I'll have to wait for a certain period of time, retrain the model, compare the previous model as well as the new model. I'll have to perform certain regression, maybe automation regression, right? And then if my new model qualifies everything, then we can update the new model. So this is a cycle. So if we see, if I want, now my aim is that I should be able to train these models to an accuracy where close to human level accuracy, right? This is the whole idea, right? That we train these models in such domains so that tomorrow it can reduce the manpower for us, maybe actually not in the bad way, but definitely there are a lot of people who can actually utilize their time even better, and a lot of manual work could be reduced. So what happens is then this complete cycle completely goes on and on and on. There are a lot of people that you put into, there are a lot of money that you put into, and what happens is it takes a large amount of time to train these models, even when we have all the technology available. So basically, because humans are coming into picture, we are reviewing the data, it's a tedious task and everything. So what do we do? So as I told you that all of this AI is passive AI. And what is the solution to it? The solution to it is self-evolving AI. And here is a small example. So you know what this is happening? So basically this is AI that is an autonomous AI. It is trying to build the best aerodynamic design for a drone automatically. It doesn't have any knowledge previously of how the drone should be, but yeah, I did not run this, right? So basically, you will have to give it an ideal situation, that this is the ideal situation. I want you to break these equations if you can, right? And then it started self-learning, it started self-evolving, and this is what it resulted into, And a strange part is that this is also this shape of a flying squirrel hip bone. This is also the design. So basically, even our nature is evolving, isn't it? Our nature is evolving, right? Everything is evolving. The nature, the universe around us is actually working on an evolutionary algorithm that we do not understand as of now. We may understand it in future, but yes, it is complete evolution. Right. So as I told you, what is passive AI versus autonomous AI, right? Passive AI is simple. You will have to tell it to do something, and that's it. It will stop, right? Alexa, if you say something to Alexa, it'll do that for you, but that's it. It will stop, right? The learning, I mean, if something has gone wrong, you'll have to wait for a certain amount of time to get it right because you'll have to go through the human feedback loop and everything and everything. And common use cases like, as we see, chatbots are again passive. Recommendations engine that you see on Amazon, Spotify, everywhere, again, they're passive. Basically, they have been arranged on certain set of data. And what could be autonomous? Self-driving cars are there. It is actually autonomous AI, right? And drones, basically, that are flying. Some of the drones have started using this technology. Now, the whole point of this discussion is how do we bring this to our business, right? And I'll be presenting all of this thing with certain stats. There will be certain stats. I won't be talking in air. There will be certain research backed from big giants like Meta, DeepMind, Microsoft Research, right? So, and yes, it is, the autonomous AI is going to be very complex. Obviously, for complex problems, we need complex solutions. Now, what are the various, first we'll just see what are the various techniques that we have for self-evolving. Basically, we have a lot of techniques, like we have Monte Carlo search, right? And meta learning is there, online learning. So these are various algorithms that are present. I'll be discussing the exact algorithms also at the end of the slide, right? So basically, there are various ways by which we can make your current AI into autonomous AI, into self-learning mode. It converts into evolutionary mode, right? Is this something very new? Not really. I mean, yes, the approaches are new. Some of the ideas are new, but the core idea is not new. So basically, this is something that has been happening in deepfakes also, but not clearly with a different model. So basically, in deepfakes, we are at a level where it becomes difficult to differentiate between a real image and a fake image, right? So basically, how is it happening? So it is actually happening if you see that there is a discriminator model, evolved here, right? So this discriminator model, what it does is, first, our generator will generate an image. And once that image has been generated, it will be evaluated by discriminator. Discriminator job is just to say that, yes, this image looks real and this does not looks real. This is its job, that's it. It provides a feedback. There are other, down the line, there are various other operations that it does, but in overview, this is what it does. Now, discriminator provides the feedback to our main generator model, and generator model keeps on improving till a time where the discriminator also gets fooled. That is, now the discriminator says, okay, this looks like a very real image. So generator has successfully generated an image that looks like a real image, right? So we'll be using a similar kind of tech here, but before I take you through the technical journey, a small experiment I just quickly performed to show the power of basically reinforcement, or this is basically genetic algorithm that I have used. Now on the left hand side, if you see, there's a video where the agent is trying to run the Flappy Birds. Can you play the video? Right. On the left hand side, we have, it is trying to learn the environment. I mean, it does not knows anything about it. So what I just did is, I just gave it 30 minutes and I just went for a coffee, and it kept on evolving itself. It kept on like learning itself, right? And then if you see on the right hand side, this is what is the result after, what, 30 minutes? You know, after 30 minutes, do you think that, in how much time can a human achieve the right hand side results? What do you say, guys? How much time will it take? That AI can do all one day, right? Right. So basically, if you see that it is already, if trained right, if provided with the right environment, if provided with the right parameters, it can surpass human capacities very easily in less amount of time. It takes less amount of time to learn, but yeah, obviously we are soon getting, we are slowly getting to that point. We are not there yet. Right, so this is one of the ways I am basically discussing, right? There are various other ways also that have been discussed. Now, basically what is happening here is that there is a decision-making model. It is very simple architecture. There's nothing complex. There's a decision-making model, and this decision-making model, the result of the decision-making model is evaluated by evaluator. Evaluator's job is to say, okay, your output looks good, or it will say your output doesn't looks good, right? It evaluates, and it can also evaluate on morals, ethics, right? I heard a lot of discussion around here happening around that the models nowadays are sexist and stuff like that. And so basically, yeah, you can have an evaluator saying that, you know what, you're not supposed to pass anything that has so-and-so things. And then we have an observer model. So basically what our observer model is doing, observer model is basically collecting the feedbacks from everywhere. One of the source of feedback is the evaluator model. The other sources could be sensors, it could be anything, right? In self-driving car, it is sensors, or it could be even a human feedback. But yes, the whole idea is to reduce human feedback as little as possible, so that we reduce the human efforts as much as possible. Now, this is basically, I will be going towards a result of one of the experiments, wherein the model was basically, there was an evaluator model used, there was observer used, and then basically the learnings were sent back to the model, right? Now, there is also one more point to consider here, that when the learnings go back to the model, it has to be done in such a way that the existing model should not be brought down, right? Ideally, this should be the case. And this is again an area of research. In the previous slide, I have mentioned few of the points. If you see, it can basically update via policy gradients, retraining, tamers, paro. These are some of the methods that are available. And this is an area of active research. But yeah, now commonly for normal programs, policy gradients would suffice. So this is what this is, that a baby gets turned into scholar via self-evolving model. So basically, there's a baby that starts, and there are basically 3 iterations of self-evolving that has been used. The initial, if you see, it has an accuracy of 24.49, and this is self-evolving, not very much human intervention required. And then we let it self-evolve, and then it goes from here to here and ultimately reaches 31.31. So basically, yeah, we can definitely say that these are not the ideal results. But yeah, this process, when keeps on happening for a certain amount of time, basically it will make your AI so intelligent that one day you will be taking sessions from an AI cyborg, right? Cool. Yeah, this is the same architecture that basically that I was explaining previously. The architecture actually says that you are basically arranging all of these models, evaluator model and observer model. I will not deep dive very much into it because it goes into technicalities. However, back, I guess, on 25th of September, or in August, 25th of August, Meta released a model called as Shepherd model. How many of you know about it? The Shepherd model? Cool. Right. So Shepherd model is a critic model. Now, its only job, it is actually a version of Llama. So its only job is to just provide the feedback, and that too, feedback with evidence. Now, this is one of the ways I'm discussing it. There are various ways this can be done. But yes, I am actually following the same pathway that has been released via Meta and DeepMind and Microsoft Research. So basically, what is happening here is you give an answer. Now, the feedback model has to provide evidence that if your answer is correct, what is the evidence for that? If your answer is wrong, what is the evidence for that? Right? So basically, the critic model will only do what it will do is it will just collect the evidence and say that, okay, this looks good, okay, this looks bad. Now, obviously, there can be a question that what if this critic model goes wrong? Definitely. But training a critic model is easier as compared to training the main model of ours. Right? This is the whole idea. Right? Now, this is again one more case study that what it says that, this is a math problem taken from a data set. And then on the left-hand side, basically, the critic model has gone wrong, actually. Right? And then when left for self-evolving, so basically, in the difference between left-hand side and right-hand side is that only the critic model was trained. Now, basically, if you see that it is giving you complete steps. It is giving you evidence. Basically, these are the evidence. And these evidence can actually vary depending on the problem you have. For legal problems, the evidence could be different. For insurance domain, the evidence could be different. But the whole point of these evidences are that, yes, the model should understand that this is where I have gone wrong. It should be able to accept these evidences that, okay, this is where I have gone wrong. This is what I need to improve. These evidences actually were also used for refining the input. I mean, that is the output that we obtain from one model. So we refined them automatically via another model, and then we send it to the learning. So the data sets that this experiment has been performed is GSM 8K. This is a very popular math data set that has been used. And the model that has been used is Vicuna 7B, and the critic model that has been used is GPT, right? So in this case, just to simplify the things, we used a GPT model, that is critic model. And then all of the self-evaluation, it happened by itself. And after certain self-evolution, self-refinement, that is, the self-refinement is basically the data is getting refined by itself. I mean, with only what we did was just to fine-tune the critic model, right? And the results are, see, from 16.43, 32.3, 32.22. And for SVMP dataset, it's 36.40 to 51.20. Quite impressive, actually. In order to achieve the same level, if you would have done using human feedback mechanism or whatever, labeling and all sort of things, you would require a lot of manual labeling. Manual labeling is a great pain, right? So this is what this pain is getting relieved via this solution. Now I hope I have delivered an idea that what we are trying to solve here. Is it right, guys? Right? So what we are trying to solve here is evaluation of AI. Basically, it should evolve itself. Now, basically, can you just put on your thinking caps and think of the use cases it can be used for, right? Just think of use cases, any use cases from your organization, any of the dream project that you want to build, or maybe the future startup, right? How many of you hold the dream of maybe starting a startup in future? Everyone should be up, right? Right. So basically, if you take any model, if you train it on any domain, and if it specializes on a specific domain, after 1.5 years or 2 years or so, your model will be better than most of the general purpose models available there, right? So, yeah, I mean, it can be used for a lot of things like workflow automation. Workflows are there in every organization, right? And some of the workflows are not really optimized. For operations, the cost operations, these cost operations are really not optimized and they're costing company a lot of money. So basically now what it is happening that AI can design a strategy that was never seen before. However, it comes with a question, can this evolving AI make such strategies that it was never trained on? What do you think, guys? Can it do? Yes or no? How many say yes? Oh. And how many say no? No. Okay. It can be done. And it has been done in past. But yes, I mean, the key here is the proper training. The key here is proper feedback, right? After a time, the AI starts building strategies, it starts building solutions that it was not trained on. This is the whole idea of artificial intelligence, that it should guide us with the new realms, right? And then it can be used in automated customer support, knowledge bases, solving tickets, technical tickets, and we will be using it for contracts, obviously. So, right, this is one of the, again, use case from business that I pulled out. Now, this is what we are trying to achieve, right, using this autonomous AI, because obviously, so the current idea is that, let's say so contracts are the DNA for any organization, right? Isn't it, guys? Right? Not the employee contracts, right? We won't talk about it. Don't worry, right? We'll talk about other contracts, right? So yeah, I mean, these contracts are the DNA for any organization. These define the policies of the business. They influence the policies of the business, right? Now, let's say I did sign a contract with an organization saying that, I will be saving the data in US region only. Your data or the data around will not leave this US region. I signed the contract and it's sitting into my database and I forgot about it. 8 months, and there are many more contracts that have been signed. And after 8 months, there is a new contract saying that, hey, you'll have to store your data in European Union countries or in specific region. And I don't even remember that this 100-pager contract I had signed, and I don't even remember saying that I had signed any such clause. But what if it is autonomous AI? It should give me a warning immediately saying that, you had already signed a contract that is not in compliance with the previous contract you had signed, right? And here comes the automatic decision-making capacity of AI, right? Now, so basically the whole idea was basically how we bring this whole thing to decision-making, right? Now, this decision-making, now, I mean, sky is the limit. You can think of lots of use cases where this automatic decision-making or maybe better than humans decision-making can be made. Obviously, as of now, currently, we are just seeing a start, right? And OpenAI does not use this, obviously, they are already using advanced methods as compared to what I'm even explaining you, right? They are using advanced methods for even training ChatGPT. They're not doing it via humans, just via humans, right? So, right, and then again, the decision, it can be a recommendation. We do not have to just let AI do everything. It can be our assistant, right? It can be recommending us a lot of new solutions, right? A common use case, I mean, because I had to put this up because this is one of the most classical example of an AI that has evolved into something very wonderful. That is the DeepMind Go application that we have. And the DeepMind Go application, basically, it was initially trained, the moves were, now basically why this example here? The whole aim of this example is that the DeepMind has so many permutation and combinations that it is more than the number of atoms that can be arranged in the universe, right? Fair enough, a very complex problem. So this is the reason that this is a very complex game where number of permutation and combinations are just too high. And guys, any problem in this world can be actually thought in terms of permutation and combinations and probability, right? Now, basically, what happened was initially they trained this model, and it was basically, it was again an evolutionary algorithm. So basically, when they trained it model, they trained it by taking some inputs from the champions. After a while, after learning itself, it evolved itself. It uses Monte Carlo tree search algorithm, and then it was able to beat everyone in the world. And not just that, it came up with such innovative steps, opening steps, and various such strategies that were never heard or thought of before. Right? It was never heard or thought of before. So yes, it will be happening, it is happening that AI will come up with these kind of solutions, strategies that human mind cannot think. Basically, it is all about probabilities, right? We have a limited capacity. We cannot think of so many probabilities. Even if we start noting on the paper, it would take us lots of amount of time to just think of those probabilities. Computers are good with computations. And basically, next leap can be seen when we actually see quantum computing into picture, right? And so quantum computing will actually, the current drawback we are facing is that we are just getting over with the computations. Yeah? Competition is not cheap, basically, it's quite costly, right? But yes, I mean, in forthcoming years, we see a lot of things happening. Right. So what are the various evolutionary and decision-making algorithms? My favorite one is actually Monte Carlo tree search, because a very less heard algorithm actually, basically, but one of the most powerful algorithms when trained right. Genetic algorithm, when trained right, basically they can do wonders, and they're already doing wonders for a lot of applications that are used across. It doesn't have to be large language model always solving your problem, because there is no point of just taking a cannon and shooting a tree to cut down the tree, right? You'll have, for smaller problems, you'll have to choose smaller models, smaller algorithms. They don't even need GPU many times, right? But they perform very well. Genetic algorithms is definitely one of the very good algorithms. Neuroevolution is again one such example. Now guys, if you notice that the complete example of genetic algorithm was playing on browser, right? It was just playing on browser. Okay, I just embedded a video, but the complete training just took place on browser. That is, it took so less resources, right? So these are some of the algorithms. And then, however, this complete discussion does not end with, you have collected everything. Observer is getting the things right. Critical model is getting the things right. What's next? Your model has to learn on the fly. It has to learn then and there itself, right? So now, as of now, what is happening? We take the data, we train, and then we wait for a certain amount of time. Then we retrain it, right? And after retraining, basically, we again update the model, right? But however, where the future will be heading towards is that the model will be updated there and there itself. And what are the ways? Yes, as of now, this is an area of research. Basically, policy gradient method is one of the ways, but it is having various disadvantages also. It is slow, and there are various other things. But yes, it is evolving. Basically, policy gradient method evolved into distributed policy gradient. I guess that's not mentioned here. Yes, it got evolved into distributed policy gradient methods. So there are various methods that are evolving. Hugging Face has recently published, it is doing a very wonderful job in coming up with libraries for solving just this problem. They have a module of RLHF, and this RLHF is actually taking a next step with a lot of new research they are doing. And even DeepMind has released a paper on all of these things. Now guys, all of this thing, what I talked before you, is it all cooked up? No, it is not. All of these results are real. So basically, when I was trying to tell about my topic to many people, so it sounded like this is just like any, you're coming up with any random new name, just to enhance the marketing, but that's not really the case. This is actually the active research. I collected the recent research of 1 to 2 months, and I came up with all these. And personally, we are actually working over it. And in future, we wish to publish a research paper also on these things. So basically, as I said, the research is not very old, right? These are the papers. You can go ahead and read it. I would say you should definitely read it, right? From Microsoft Research. Self is again one model. Self-evolve is model that is actually, self was based on self-evolve. Shepherd was a Critic model. I got the date wrong. I said 25th of August, but it's 9th of August. And then we have a model from DeepMind. And then on 3rd of October, actually, AutoGen was released. AutoGen is actually how you are using multi-agents, that is multi-models. They should be able to communicate with each other. That is, this is what we have demonstrated. They should be communicating with each other to develop reasoning and to solve more complex problems. So basically what we are trying to do is we are trying to reduce the human in loop. We're trying to automate all of this stuff. So guys, now we'll be open for question answering, but I would like all of you guys to connect me on LinkedIn. I'll be sharing my slide deck over there. And definitely I'll keep you posted with all of the new research that is going on. Although in past, I did not used to post much, but now recently I have started doing it, right? So guys, now all open for all of the question and answers.
So one of the questions I have is, you talked about these two models, right? Decision-making model and observer model, isn't it? Can you give a practical example of how it will work for a much more fundamental task like, let's say, text classification, right?
Right.
What I can think of before this session is that if you have a text classification, let's say you're using a model, maybe you're using a model right from scratch or a fine-tuned model, all you can is automate the training pipeline and the model will keep updated, right? I'm trying to connect how this will work, a much simpler task like a text classification in this evaluator and observer model. How is it like they're just two models, they work in tandem, or it is much more
so yeah, I mean, text classification is quite an easy way. I mean, this is quite a simple use case. Yes, obviously, let's say the text classification is taking place, and now you are worried if the text classification is right or wrong. So basically, you can put on observer model. You can even choose to put in a large observer model for certain amount of time. Okay. Let's say you choose that, okay, these are my 10,000 responses. You will have to evaluate them for, and those will be evaluated in few hours itself, right? Whereas human would have taken a lot of time. And now this observation, this new result goes back into the model, right? This whole complete results that you have from the observer model, this observer model will also give you the new data to train. So I was explaining about refinement of the data. That is, it should also give you the new data to train. And this new data, you just have to collect it and you have to train your new model. That's it.
So anyway, sir, in my typical production system, I will have my evaluator model, which is supposed to work the way it is, right? It is just an observer model. What it will do, it will additionally evaluate whether you are making the right decision or not. Right. But it's also going to help you give more data points, because many a time we don't have data points enough for us to train our model, right?
Right. AutoGen is again the recent one that I said. AutoGen is actually a wonderful platform. They have created a kind of semi-platform for all of these things. So basically, you want to interact between various models. They want to interact with each other, and what kind of prompting. There is specific technique called metadata extraction from the critical model. That is the complete set of evidences it will give you that why this result is right or why this result is wrong. And then based on that, we take that data and we push it back into the main model.
Okay, got it. Thanks.
Anyone else, guys? Yeah.
for the task where we don't have a labels. However, your evaluator model needs to be trained with labels only, right? So still there is a restriction that
Yes.
you should first train the evaluator, train the observer.
Correct.
So
Basically,
yeah.
let's say if earlier number of hours of labeling required were 100 hours, now it will reduce to 8 hours, 9 hours. So this is the optimization that we gain, right?
Okay. So it's like it's just accelerating.
Yeah,
your
basically
development.
the whole idea was, let's say if you want to train a model to, you want to make your model as far as with human reasoning and stuff like that, it would usually take, I calculated it for my use case, and I was like, this is going to take me at least 1.5 to 2 years if even if I employ a lot of people and just for the labeling stuff and all. And so I kept on thinking what could be the better way. So using this kind of technology, we could reduce that time to 3 months or 4 months. So just imagine 1.5 to 2 years, the amount of cost involved and everything, and now you're just reducing that time to 3 to 4 months with a very small team again.
Okay. Thank you.
Guys, that's it.
Advent of quantum computing, there would be, we could do more things with this technology. Could you state some examples of what could be the
Yeah, basically I could give a different talk separately on quantum computing, and I love this topic actually. So basically quantum computing, where this quantum entanglement is going to speed up the process. And the wonderful part is we still don't understand how quantum entanglement works. But yes, the speed increases multifold. Now basically, let's say I'll give you an example of weather forecasting. For weather forecasting, we need proper weather simulations. Now first, we need to understand that any problem in this world, you give any problem in this world, it can be converted into mathematical problem. We need to convert any problem can be converted into mathematical problem. Let's say about weather simulation, right? Now there are so many factors involved in weather simulation that as of now we are using supercomputers for predicting that, but we are not able to do that. We're not able to reach to that point because of the computational limits. I mean, our hardware is not able to compute so many equations. It is not able to compute so many probabilities, right? That can occur in nature. So once the quantum computing comes in, these kind of problems, let's say about exploring more about physics, there are a lot of things that we need to explore about physics. Then about weather simulation is one such problem. Now, any big problems that we are not able to solve as of now, we should be solving that with quantum computing.
Thanks.
Right? Yeah.
And when I attended your talk, it seems that it can be solved. So I just want to take your thoughts on it.
Sure.
So we have built a conversational chatbot using LLM 30B model. Now,
30 billion.
30 billion.
Right.
And multiple versions we checked for Alcan and MPT 30B as well. Llama is the one which is giving much more better results.
Right.
Now, next question that we are being asked is that how do we make it self-learning? In terms that, first, how do we make sure that a user can give a feedback to it, which we have not been able to encounter? It's a one-way conversation.
Right.
Only the user can able to do is that ask better refined question, which is prompt, and then coming back.
Right.
But how do you give that response back that the response is not at all correct? Thumbs up mark, even if you give it. How do you account that take back as an input into your model and refine it?
So yeah, I mean, the exact solution for you is RLHF library. That is, I am not getting the exact name of the library, by Hugging Face. They are solving this exact problem. So you can just take that model, you can just take the input from your users, and you can actually update your Llama model then and there itself. This is already happening.
Okay.
Right?
So should we ask user to tell why this answer is not correct? Or is this
user
only
will not provide that feedback. User will never do that.
Internal organization, maybe we can have some incentive program to
actually start playing with this Shepherd model. It is specifically for Llama. It is a variant of Llama. So basically, Shepherd is just a critic model, just designed for observing the output that your model is producing.
So in the Shepherd also, when you said that while the answer is not correct, the user will have to respond back with the.
That we will have to do it.
We'll have to do
That
it. So
we'll
we'll have
have
to
to do it.
eventually pass back that feedback.
Right. So eventually, the same thing that I said earlier, like if we were using for the same use case, the let's say 1,000 hours would be required to reach to a certain level. Right. Now that would be reduced to 100 hours or so. Right.
Okay.
So a huge gain in efficiency will be there.
And any in terms of
and one more just suggestion, 30 billion is a very huge model, right? For specific tasks, you can actually just run on 7 billion, 4 billion models. You don't need 30 billion is pretty large model. So again, it once it is trained properly, it will actually bring down the costs for the organization.
yes, that we have seen. So right. In fact, evaluated multiples, but 30
I know,
is accurate.
because that will be giving the best pre-trained results.
Pre-trained results.
I understand.
In fact, one challenge, but before I digress to another topic, actually I've lost the thought completely. Let's come to another topic. Is that even in what we've seen is that when we train the model on set of documents, say 30 to 50 documents, the model was performing very well, right? And in the banking context, I come from a banking space where products will be of similar nature. Say for credit card, for example, you have Regalia and Diners and other cards. There'll be differences in the features, benefits that you offer to customer, but most of the policies and other things will be similar, right? Then when we started adding more and more document in the repository, the efficacy of the model response started deteriorating.
So you want your model to have the knowledge of complete repository.
Yes.
Right?
Yes.
So, I mean, yeah, RAG is that technique. And there was, I guess, one session also.
The session was there.
Right.
So, but I'm trying to understand, as you're adding more and more documents, it should, in fact, improve.
No, but that has to go into learning, actually. And one more point is that there are two things that a model can learn. First thing is, let's say we are taking any pre-trained model. Yeah. If we are training with anything, it is losing its existing learning. Point one. Point two, domain-specific training. Domain-specific training is you just dump the set of documents towards it. However, once you are doing it, these models like Llama 2, Falcon, these are instruction fine-tuned model. Okay. They lose the ability to reason if you are simply putting the documents. So idea is that you take some documents, right? You dump those documents, as well as what you do is you prepare basically comprehension type of data sets. That is, you prepare instruction. So basically, any fine tuning that has to be done should be done with instruction fine tuning always. Instruction fine tuning plus the documents. Okay. Because any learning that you push into the model will be unlearning also something.
Right. So that manually instruction fine set if you to create for each of the document, it suggests maybe a metadata or kind of a separate metadata for the document.
Yes, I mean you can make that, and basically if you are making for a specific, let's say if the use cases are limited, these instructions can be even generated actually. You can generate it via ChatGPT-4.
Okay.
Right? There are specific plugins that just do that generate the data for you. If the data, but you will have to be careful that these documents will then go to OpenAI server.
A lot of talk about genetic algorithms and all the evolutionary algorithms that we have. So I have been closely working with genetic algorithms to solve the problem of speed cubing. So now if you're aware of this is not exactly a speed cube, but this is a pyramid cube. There are 43 quintillion combinations that we have for this. Right now, what we are trying to do, we have speed cubers, we train them, but there are a lot of human parameters still involved.
Correct.
Like the palm, the size of my palm that I'm going to have, the strength of my fingers, and how exactly can I combine this. And then the feedback loop that we have. There we have questions from speed cubers like, if we are more comfortable with some moves rather than other moves. So these sort of questions and the feedbacks that we have from speed cubers still involve human
So basically what you're trying to solve is come to a solution.
Solution, yes.
For the,
There is a certain God's number that we have. We need to reach that particular speed, and we need to reach that God numbers in order to get my solution working. So that is what we are trying to solve.
Correct.
But the problem is we still require this human intervention. So how exactly? I'm currently using genetic algorithms, but this is only to reach the God's number. We are still not able to get that human element out. I still require some speed cubers to come and have training on my current solution.
Yeah, then basically the basic data set that we have taken may not be sufficing the use case as of now.
Okay.
So basically the data set that we prepare for first time training the model, that is
There are sensors that we have, images that we have.
so let's say even in this genetic algorithm that that I did show you, basically we did provide it an environment. Now basically you can actually take it to a simulation mode also. You
Yes.
have to prepare a small simulation
Yes.
thing, and there basically you can just set that these are the best things, these are the best parameters that we need to reach to. You can actually play with Monte Carlo tree search also.
Yeah.
And because it has shown really awesome results in all of these things. And yes, I mean, for certain amount of time, hand holding should be required. But if these models are requiring hand holding for a larger amount of time, then we are not doing something right. Yeah.
Okay.
There is something not right getting. I mean, maybe the data set, plain data set.
No, but it actually is a customized, there are a lot of customization because every speed cuber that we have coming in that actually uses the algorithms that we provide, it requires certain sort of customization from their end as well. There are certain sort of moves, we have certain set of moves, B2, D2. Those moves are actually, they say that, no, this is much better. We can do a combination. So there are certain inputs that we always require for them. So this self-evolutionary thing that...
But if you are using genetic algorithm, after a time it should start suggesting you the solution itself.
Yes, it does. But
Right.
still out of those
fails,
suggestions...
it fails certain times. And
yeah.
then you say the human actually outsmarts it.
Yes.
So basically the whole idea is the implementation. I guess, I mean, if implementation done right, and for certain amount of time when we put the data into it, it should be able to evolve. This is the whole idea. And I strongly say that you should be actually trying with Monte Carlo tree search.
Yeah, I'll be
because
trying that.
I mean, the whole DeepMind Go was built on this. The best chess engines are working on this. So the gamification thing.
Yes.
And then not just that, I do not know, have you ever tried, there are actually 12 variants of reinforcement learning.
Yes.
Right?
Yes.
And then there are a lot of things that could be done there. Now let's say if your problem is too complex to fit into these algorithms, we can actually dive towards neural networks being used as reinforcement learning.
Yeah, I've tried them as well, but no results
Okay,
whatsoever.
so yeah, we can definitely connect.
Yeah.
And
Yeah, let's connect around
sure.
this. Thank you.
That's it.